Imagine you have a bunch of building blocks stacked up on a flat surface. Your challenge today is to figure out the total exposed surface area of all those blocks combined. Take a moment. What would you do to count every visible side? Alright, let's dive into the problem. We're given a two-dimensional grid, which you can think of as a blueprint for a city of cubes. Each cell in this grid, at a specific row and column, tells us how many cubes are stacked vertically at that exact spot. So if the grid has a value of, say, 3 at row 0, column 0, it means there are 3 stacked cubes there, one on top of the other. All these cubes are 1 by 1 by 1 unit in size. Our goal is to calculate the total surface area of all the cubes that are exposed to the outside world. This includes the top, bottom, and all 4 side faces of every cube that isn't covered by another cube or by the ground. Let's look at an example. Imagine a simple grid. Row 0, column 0 has 1 cube, and row 0, column 1 has 2 cubes. The 1 at the first position means 1 cube is stacked there. It has a top, a bottom, and 4 sides, giving it a total of 6 faces. But wait, if it's sitting on the ground, its bottom face isn't exposed. So it has a top and 4 exposed sides. Now for the 2 at the next position, meaning 2 cubes stacked. The bottom cube has its bottom covered by the ground, its top covered by the cube above it. It has 4 exposed sides. The top cube has an exposed top and 4 exposed sides. Notice how the faces between stacked cubes are not exposed. This is what makes it tricky. Also, if 2 stacks of cubes are next to each other, like the stack of 1 next to the stack of 2, they share a common wall. That shared wall is not exposed, so we only count the parts of the wall that stick out. The problem constraints tell us that the grid will be square, meaning it has the same number of rows and columns, and its size will be between 1 and 50. The number of cubes at any spot will be between 0 and 50. A 0 means no cubes at that position. The most straightforward, or brute force, way to approach this problem is to think about each individual cube. For every single cube that exists in our 3D structure, we could try to determine if each of its 6 faces is exposed. We would iterate through every cell in our grid, and for each cell, if there are h cubes stacked there, we would then iterate h times, effectively going through each individual cube in that stack. For each cube, we'd check its 6 faces, top, bottom, north, south, east, and west. For the bottom face, we'd check if it's the very first cube in the stack. If it is and it's not sitting on another cube, then its bottom is exposed. For the top face, we'd check if it's the very last cube in the stack. If it is, its top is exposed. For the side faces, north, south, east, west, we would need to look at the neighboring cells in the grid. If there's no neighboring cube at the same height or higher, then that side face is exposed. This approach is conceptually simple because we're directly modeling the physical cubes. However, it's inefficient. Why? Because we're doing a lot of redundant checks. For example, when we check the north face of a cube in one stack, we're essentially checking the south face of a cube in the neighboring stack. We're doing similar calculations twice. We also iterate through each cube's height, which can be up to 50. If our grid is 50 by 50, and each stack is 50 cubes high, we're doing 50 times 50 times 50 operations in the worst case. This makes the time complexity roughly n squared times max height, where n is the grid size and max height is the tallest stack. The space complexity is simply constant because we're not storing any extra data proportional to the input size. The key insight to optimize this problem is to realize that instead of counting each face of each individual cube, we can count the asterisk total potential surface area and then subtract the areas that are covered. Think of it like this. Every single cube by itself has 6 faces. So if we have h cubes in a stack, they contribute h times 6 to the potential area. But then we subtract faces that are touching. This means we'll count the exposed area directly by considering each stack and its neighbors. Let's walk through the optimized approach. We'll start by declaring a variable called total area and initialize it to 0. This variable will keep track of our running total. We'll then use two nested loops to iterate through every single cell in our grid. The outer loop will handle the rows. Let's call the current row index I. The inner loop will handle the columns. Let's call the current column index j. Inside these loops for each cell, we first get the height of the cube stacked at that position. Let's call this current height. Now, if current height is greater than 0, meaning there are actual cubes at this spot, we immediately add 2 to our total area. Why 2? Because every stack of cubes, no matter its height, always has one exposed top face and one exposed bottom face, assuming it's sitting on the ground. These two faces are always there if there's at least one cube. Next, we need to consider the 4 side faces: north, south, west, and east. Instead of checking each cube's face, we'll calculate how much of the current stack's side is exposed to its neighbors. For the north face, we check if we are at the very first row. If I is 0, it means there's no row above us, so the north neighbor height is 0. Otherwise, the north neighbor height is the height of the stack in the cell directly above us, at grid position I-1, j. We then add to our total area the maximum of 0 or current height minus north neighbor height. This effectively counts only the parts of the current stack's north face that are taller than its northern neighbor. We do the exact same logic for the south face. Check if I is the last row. If so, south neighbor height is 0. Otherwise, it's the height at grid position I+1, j. Again, we add the maximum of 0 or current height minus south neighbor height to total area. We repeat this pattern for the west and east faces. For west, if j is 0, west neighbor height is 0, otherwise it's grid at ij-1. For east, if j is the last column, east neighbor height is 0, otherwise it's grid at ij+1. In each case, we add the maximum of 0, or current height, minus the respective neighbor height to total area. After iterating through all cells, our total area variable will hold the final answer.
Let's trace this optimized approach with our example grid. Row 0, column 0 has 1 cube, row 0, column 1 has 2 cubes, row 1, column 0 has 3 cubes, and row 1, column 1 has 4 cubes. Our total area starts at 0. We begin our loops. First, I is 0, j is 0. The current height at grid 0, 0 is 1. Since current height 1 is greater than 0, we add 2 to total area. Total area is now 2. Now for the neighbors. For north, I is 0, so north neighbor height is 0. We add the maximum of 0 or current height 1 minus north neighbor height 0, which is 1. Total area is now 3. For south, I is 0, not the last row. South neighbor height is grid at 1, 0, which is 3. We add the maximum of 0 or current height 1 minus south neighbor height 3. This is 1 minus 3, which is negative 2. The maximum of 0 or negative 2 is 0. So, we add 0. Total area remains 3. For west, j is 0, so west neighbor height is 0. We add the maximum of 0 or current height 1 minus west neighbor height 0, which is 1. Total area is now 4. For east, j is 0, not the last column. East neighbor height is grid at 0, 1, which is 2. We add the maximum of 0 or current height 1 minus east neighbor height 2. This is 1 minus 2, which is negative 1. The maximum of 0 or negative 1 is 0. So, we add 0. Total area remains 4. Now, I is 0, j is 1. Current height at grid 0, 1 is 2. Since 2 is greater than 0, we add 2 to total area. Total area is now 6. For north, I is 0, north neighbor height is 0. We add the maximum of 0 or 2 minus 0, which is 2. Total area is now 8. For south, I is 0, not last row. South neighbor height is grid at 1, 1, which is 4. We add the maximum of 0 or 2 minus 4, which is negative 2. Max of 0 or negative 2 is 0. Total area remains 8. For west, j is 1, not first column. West neighbor height is grid at 0, 0, which is 1. We add the maximum of 0 or 2 minus 1, which is 1. Total area is now 9. For east, j is 1, which is the last column. East neighbor height is 0. We add the maximum of 0 or 2 minus 0, which is 2. Total area is now 11. Next, I is 1, j is 0. Current height at grid 1, 0 is 3. Since 3 is greater than 0, add 2 to total area. Total area is now 13. For north, I is 1, not first row. North neighbor height is grid at 0, 0, which is 1. Add maximum of 0 or 3 minus 1, which is 2. Total area is now 15. For south, I is 1, last row. South neighbor height is 0. Add maximum of 0 or 3 minus 0, which is 3. Total area is now 18. For west, j is 0, west neighbor height is 0. Add maximum of 0 or 3 minus 0, which is 3. Total area is now 21. For east, j is 0, not last column. East neighbor height is grid at 1, 1, which is 4. Add maximum of 0 or 3 minus 4, which is negative 1. Max of 0 or negative 1 is 0. Total area remains 21. Finally, I is 1, j is 1. Current height at grid 1, 1 is 4. Since 4 is greater than 0, add 2 to total area. Total area is now 23. For north, I is 1, not first row. North neighbor height is grid at 0, 1, which is 2. Add maximum of 0 or 4 minus 2, which is 2. Total area is now 25. For south, I is 1, last row. South neighbor height is 0. Add maximum of 0 or 4 minus 0, which is 4. Total area is now 29. For west, j is 1, not first column. West neighbor height is grid at 1, 0, which is 3. Add maximum of 0 or 4 minus 3, which is 1. Total area is now 30. For east, j is 1, last column. East neighbor height is 0. Add maximum of 0 or 4 minus 0, which is 4. Total area is now 34. All loops complete. The final total area is 34.
And there's our final result. The total exposed surface area is 34. This is correct because we meticulously accounted for all exposed top, bottom, and side faces by comparing each stack to its neighbors. You'll often spot this pattern when a problem asks you to calculate a property of elements in a grid or matrix that depends on its immediate neighbors. Another strong signal is when the problem involves blocking or covering effects, where one element's presence influences the visibility or interaction of another. The time complexity of this optimized solution is O of n squared, because we visit each cell in the grid exactly once. The space complexity is O of 1, as we only use a few variables for tracking. Try solving a similar problem involving grid traversal and neighbor calculations. It's a fundamental pattern. If you found this helpful, hit that subscribe button for more DSA breakdowns.